Great movie, Angry Man. All right. My favorite, though, I think, would be Inherit the Wind. Welcome to MathStat 341, lecture 20, November 1st. And this is one of the easiest lectures for me to give. I just have to have a few keywords to remember what I'm going to be doing, and then we're going to just do computation up the wazoo. So we're going to actually write down explicit formulas for sums of uniform random variables and sums of Gaussian random variables. And hopefully this will convince you that if either you or I need to do it again or something else, we can just work through the computations. Now, as much as we love doing lots of tedious algebra and integration, if there is ever a way to avoid it, we take it. So who is our favorite New England transcendentalist writer? Thoreau, Henry David Thoreau, simplify, simplify, right? Before you do any work, always stare at it and say, is there a better way to do this than brute force computation? Frequently, the answer is yes, especially on homeworks and exams, which are not as always, truly indicative of the real world. Again, what I want to keep emphasizing is that we can frequently integrate without integrating. What does this mean? Well, if I give you a probability distribution, what two things do you immediately know must be true if it's a probability distribution? Integral is one, and it's non-negative. So imagine I have something that looks like a Gaussian. I have something that looks like e to the negative 7x squared. And I've got some other integrals around it. I know at the end of the day, when I integrate that, it has to integrate to 1. So the normalization constant of floating around have to just adjust themselves so that at the end of the day, it ends up as a probability distribution. So if I know that it's a probability distribution and I know its functional form, then I can figure out what those remaining normalization constants are. And we're going to see again and again and again how valuable this is. All right, so the first, so this picture seems to just keep coming up. All right, I must have pasted in the wrong spot. All right, so the first is sums of uniform random variables. So we've seen an example of this. If you roll a fair die, you get 1 through 6, each with probability 1/6. If you add 2 fair die, it's going to be a triangle function. For simplicity, let's assume, x1 and x2 are uniform on the interval 0, 1. So this means their densities are, say, p of x equals 1 if 0 less than equal to x less than equal to 1 and 0 otherwise. Okay, so how would we calculate x1 plus x2? So if we let x be x1 plus x2, what do we use to figure out the density of a sum of independent random variables? So what is the process that takes two densities as input and gives a new density as output? It's this is the convolution, right? So the density of the random variable x at x is just going to be, since they're the same, will be px1 convolved with px2 at x, or just p convolved with p at x. So this is going to be the integral from negative infinity to infinity of p of t, p of x minus t dt. If you think about what's going on, here's my density for the first one, here's my density for the second one. I want the sum of the two values to equal x. And so t plus x minus t equals x. Now, one of the things that makes this a little bit of a pain to deal with is I have a different definition for p depending on where x is. So if x is between 0 and 1, p is equal to 1, otherwise it's equal to 0. So when I look at the first one, if I look over here, this forces 0 to be less than equal to t to be less than equal to 1. Because otherwise, p of t is just 0. So I now have an integral from 0 to 1. And what is p of t in that range? It's just 1. So it's going to be just 1 times P of X minus T dt. And now, what must be true if I want P of X minus T to be non-zero? Where must X minus T live? So I want P of X minus, P of X minus T is, I'm sorry? Yeah, it must live between 0 and 1. If it's outside of 0, 1, then it's just going to be 0. So this forces 0 less than equal to X minus T less than equal to 1, or T less than equal to X less than equal to 1 plus T. Right? What can you tell me about these bounds for X? How large could X get? Yeah, the largest X can be as 2, which makes sense. If I have two uniform random variables between 0 and 1 and I add them, I damn well better not get something better than 2. So this is reasonable. But it means I'm going to have potentially differences depending on whether or not X is greater than 1 or X is less than 1. And so what I can try to do is I can try to figure out, okay, well, I need X to go from T to 1 plus T. But T only goes from 0 to 1. So if X goes from 1 to T, depending on what value of X I have, I could get some differences over here in terms of what values of T. So let's try to think about where we need to study things. And now what we're going to do is we're going to use some symmetry. Symmetry. I claim X equals X1 plus X2 is symmetric about 1. And the proof is as follows. What is the expected value of a sum? It's the sum of the expected values. So if I look at the expected value of X, it's the expected value of X1 plus the expected value of X2. Each is uniform 0, 1, so each has mean 1/2. So the expected value is 1. So again, this is the first question you always ask any probability distribution when you meet it. What's your mean? I could calculate the variance right now. I'm not going to. We know it's 1. Now I'm claiming it's symmetric about 1. And here's the beautiful proof. Let's let yi equal 1 minus xi. What kind of distribution is yi? So xi is uniform 0, 1. What can you tell me about 1 minus xi? Yeah, it's also uniform 0, 1. It's also just uniform 0, 1. Is it dependent or independent from xi? Absolutely dependent, right? You know the value of xi, you exactly know the value of yi. So if we study y1 plus y2, that's the same distribution as x1 plus x2. Because it's still the sum of two uniform random variables. So the probability x1 plus x2 equals sum A, which is less than 1, would be the same as the probability that x1 plus x2 equals, so let's see, here's 1, here's A, here's 0, here's 2. So this would be, I think, 2 minus A. I'm going to try to do this. Does this make sense? That basically, the distribution has to be symmetric because y1 plus y2 has the same distribution as x1 plus x2. But what is y1 plus y2? y1 plus y2 is just 2 minus x1 plus x2. So if I know the probability that x1 plus x2 equals a, that's the same as the probability that x1 plus x2 equals 2 minus it, because the distribution is symmetric. If you're not comfortable with this, you can, of course, just do the calculation for all values of x. But if you notice the symmetry, you cut your work in half. You only have to calculate what's going on for x up to 1. So you come back to this equation. And so we have our density for x is going to just be this integral. So without loss of generality, we may as well assume 0 less than equal to x less than equal to 1. Because if we know what's going on there, we know what's going on for x larger than 1 by symmetry. All right, well, we need t to be less than equal to x less than equal to 1 minus, less than equal to 1 plus 2. So because x is at most 1, do we have to worry about x being less than equal to 1 plus 2? No, we get that for free. So get trivially, x is less than equal to 1 plus t. But the other part, that t is less than equal to x, that's going to restrict t. So now the integral is restricted to t less than equal to x. Okay, and so now we get that our integral is equal to the integral t goes from 0 to x. We had a 1, and now we have a 1 for the probability of x minus t dt. This should be a pretty easy integral to do. I'm integrating the function 1 from 0 to x. What do I get? X. And so now if you plot what's going on, here's 0, here's 2, here's 1. The density goes all the way up to x and it's symmetric, so then it must come down like this. And here's the density p of x. It's non-negative, great. That's a good check. What other check could we do? So we checked, is this truly a density? It's non-negative. What's the other check we can do? Yeah, and is the area 1? Of course. Right? Geometry, right? In fact, this is really simple geometry. It's a triangle with base 2 and height 1. Yeah, it's a really nice calculation here. And now if you wanted to, you could play the game and try to calculate sums of 3, 4, 5, uniform random variables. You can keep doing these games. It's actually easier in some sense if you keep doing it in powers of 2. Because if I had 4, I can do it as 2 plus 2, and I know each one of these densities, and it's the same one each time. But the big thing you have to be careful about, caveat, is region of integration. It is so easy to have the wrong bounds. Okay, so this is how you would use convolutions to find the example. It's not so bad for the case of the sum of 2 uniform random variables. We saw a few lectures ago that as you start to do 4 and 8, it becomes a god-awful mess to write it down in closed form. And this is why we're going to prove, or one of the reasons why we're going to prove the central limit there. Because you do not want to work with something that complicated. You want to work with something that's approximately true and very easy to work with. All right, now it is time for the Gaussian. Without loss of generality, mu equals 0, sigma equals 1. Let's make my life easy. Okay? I can always translate and fix things without too much trouble. So x1 and x2 will be independent normal variables with mean 0 and variance or standard deviation 1. This is another nice reason of why you want to choose the standard deviation and the variance to be 1, because when you write it, it's supposed to be n u comma sigma squared, or is it n u comma sigma? I think it's supposed to be sigma squared. But if sigma squared and sigma are both 1, then it doesn't matter. It makes sense that it would be sigma because that's the parameter, but sigma squared is the variance. So you can make either argument. It's nice to just do n0. All right. So what can you say about x, which would be x1 plus x2? Well, the expected value of x is going to be 0, because this is just the expected value of x1 plus the expected value of x2. What about the variance of x? That'd be the variance of x1 plus the variance of x2. 1 plus 1 equals 2. So the standard deviation of x is equal to the square root of 2. Okay, so I know the mean is 0. This is clearly going to be symmetric. And I know the standard deviation is square root of 2. Does anybody know what shape Gaussian plus Gaussian is? So it's just another Gaussian. And then the question is, even if they don't have the same mean, that's not a problem, because again, the means are just additive. And I can subtract, if one has mean 5 and one has mean 7, subtract 5, subtract 7, they now have the same mean and add. The question is, do they have to have the same standard deviation? The answer is no. Gaussian plus Gaussian is Gaussian. So this is what's known as a stable distribution. Same shape when some independent elements. So then, it's very important that I'm not assuming that the standard deviations are the same, because now if I wanted to sum 3 or 4 Gaussians, I would be okay. So if you want, perhaps we should do the more general case when we have 2 different standard deviations. And so maybe what we'll want to do is generalize. So we could say maybe x1 is normal mean 0, variance sigma 1 squared, and x2 is normal mean 0, variance sigma 2 squared. This would be extremely useful, because then if I wanted to sum, say, for instance, y1 plus y2 plus y3 plus yn minus 1 plus yn, I could first sum these, get that's a Gaussian, have this as a Gaussian, and then get a Gaussian. So I wouldn't be able to do this if I only proved that Gaussian plus Gaussian is Gaussian if they have the same standard deviation. But if I can do it for 2 arbitrary ones, then I can just keep doing it by nested parentheses. So, the way you would do it really painfully is y1 plus y2 plus y3. And I can start, playing games with different colors. Plus y4, and I'll just do one more because it's kind of fun. And so if I just do it like this, just by grouping parentheses, it would be okay. So it's sometimes not a bad idea to just do the first case when sigma 1 equals sigma 2 equals 1, just to make the calculation easy, and then you do a search and replace afterwards. Or you could just say, you know what, let me just try to do the general case as long as I can. And then if things get really bad, then I'm going to say to hell with it. Let me simplify and do sigma 1 equals sigma 2. So the following question is definitely applicable to anybody who plays baseball or football. If you throw an object, assume, of course, there's no air resistance because we're playing in physics stadium. What angle do you throw it so it goes the furthest distance? 45 degrees. That's if you want it to come to the same height as when you start. Now, if you're throwing the football, that's a reasonable assumption that you want it to go roughly to the same height. You don't want your receiver to be jumping up in the air or making the shoestring catch. For baseball, that's not necessarily true, because it doesn't necessarily have to end up at the same height, you might need to just clear the fence, which is possible in pockets of the pen, right? In certain areas. And so how do you figure out where it is? Well, it's a nice calculus problem. It's much easier to find the maximum angle if the final height is the same as the initial height. If it's not, then the differentiation becomes a little bit more involved. And so I'm going through the notes to teach this to my son and his friends. And I've decided I'm going to keep it general as long as possible. And then at the very end, when we have to start doing the maximization, I said, and now we can see how painful it's going to be in general to solve. Let's do the special case when they end up at the same height. So this is really good life advice. Keep the problem as general as you can, as long as you can. How many of you think I prepared this lecture in advance? Well, let's say within the last 2 months, as opposed to I've given this at some point in my life.
Based on your intro,
Yeah.
so I think you're at least prepared for less.
Oh yeah, I have not prepared anything really for this because these are not fun calculations to do.
Normally use something.
Yeah, I mean, because this is basically, it's just do algebra. Once I know what algebra to do, the lecture essentially writes itself as long as I don't have a brain freeze. And so given how painful the algebra can be at times, I have no desire to do it beforehand. And it's better for you to see me doing this live. So xi is normal 0 sigma I squared. So that means the density, and I'm going to just write pi just to make the notation a little bit easier. Pi of x is 1 over square root of 2 pi sigma I squared e to the negative x squared over 2 sigma I squared. And so x, as always, is going to be x1 plus x2. And then p of x at x is going to be p1 convolved with p2 at x, which is the integral from minus infinity to infinity of p1 of t, p2, no, sorry, still. P. And we'll call that just, p of t. So it's going to be p of t, p of x minus t. Oh, no, I have to put in subscripts. P1 of t, P2 of x minus t dt. Okay. When we did the uniform, I had to be careful about the range of integration because the uniform had a split definition. It was 1 for inputs between 0 and 1 and negative otherwise. Do I have to worry about split definitions here? Or does my definition for pi of x, does that functional form hold for all inputs? Holds for all inputs, so I don't have to worry about the region of integration. All right, that's nice. So it's the integral, t goes from minus infinity to infinity, 1 over 2 pi square root of sigma 1 squared, sigma 2 squared, e to the negative t squared over 2 sigma 1 squared, e to the negative x minus t squared over 2 sigma 2 squared dt. Right? Do I have to write t equals? No, I've got the dt, but when I have multiple variables going around, anything I can do to just quickly be able to glance down and see what the hell is going on, I'll take. And so I'll write t equals. All right. Is my goal to find this integral? Yes. But that doesn't mean I have to actually integrate it. It means I just have to identify its functional form, especially if I think it's a Gaussian. If it's a Gaussian, it's going to be a Gaussian in terms of what variable? Not t, because we're integrating out t. So at the end of the day, it should be x. So the hope, right? Hope is it's some constant depending on sigma 1 and sigma 2 times e to the negative x squared over some function of sigma 1, sigma 2. Again, I'm just trying to set up what I think the answer should be before I do any of the calculations. I'm believing it should look something like that. All right, so as I start doing the integration, I've got this big constant outside over here. Is there a need to keep writing this every single time? No. So I'm going to just call that constant C12 because it depends on sigma 1, sigma 2. Okay. And then I have the integral from t goes from minus infinity to infinity of e to the negative. I don't like the 2 sigma squareds and all this shit in the denominator. So I'm going to introduce some new letters if that's okay, just to try to make my life easier. We okay with that? All right. So let's let AI equal 1 over 2 sigma I squared. This is going to make things a little bit easier to write. So I have e to the negative a1 of t squared, e to the negative a2 of x minus t squared dt. Okay? And so we just need to get the functional form of this. Right, so do we all agree that this is the integral we want to calculate? Yes. So let's expand the second exponent. So this is going to equal C12 integral t goes from minus infinity to infinity. Does anybody remember those old pens? They used to be like 4 colors you had on this on the top and push different ones down, and you could just change very easily. I wish I could figure out how to do that so fast over here to just keep different colors. E to the negative a1t squared, e to the negative a2 x squared minus 2 xt plus t squared dt. Right? Now, I only care about integrating with respect to t. So then e to the negative a2 x squared, I can just pull that outside. So this is just going to be C12 e to the negative a2 x squared integral t goes from minus infinity to infinity of e to the negative a1t squared negative a2t squared, and then it's going to be plus 2 a2xt dt. Okay. So C12 e to the negative a2 x squared integral t goes from minus infinity to infinity e to the negative, and then it's going to be a1 plus a2 times t squared. I'm pulling out a negative a1, a2, so it's going to be minus 2a2 over a1 plus a2 xt dt. So far, so good? Yes? What does this look like in the exponent? Doesn't this almost look like e to the negative constant, like t minus mu squared? This is the complete the square. If this was t minus mu squared, well, then I could just translate t, and this would be the same as integrating just t squared. So looking like t squared minus 2 ut plus mu squared minus mu squared, which would be t minus mu squared minus mu squared. And then if we have the integral of t minus mu, even though that mu depends on x, we can just translate it away. So here, mu is going to be a function of a1, a2, and x. But I'm going to just complete the square. And when I complete the square, I can then translate and I'll have an t integral that will be independent of x. So is everybody clear on the broad brushstrokes of what we're trying to do? That this is going to just be C12 e to the negative a2x squared integral t goes from minus infinity to infinity e to the negative a1 plus a2. And then it's going to be t squared minus 2a2 over a1 plus a2. I'll put the x up here, t. And then it's going to be plus a2 x over a1 plus a2 squared minus a2 x over a1 plus a2 squared dt. I basically added 0. And by adding this, this is just t minus a2x over a1 plus a2 squared. Right? And so this is going to become e to the negative a1 plus a2 t minus, let's call it mu of a1 a2 x squared e to the negative a2 x over a1 plus a2 squared. So we all are comfortable in how we got here. Does the second factor here, does this have any t dependence? We can pull that outside the integral. This part over here, does this have x dependence? Hell yeah, right? It's 2a2x over a1 plus a2. This has x dependence. But we're integrating t minus mu of this square. I can then just change variables. I can then just shift t to t plus mu and remove all that. So this is going to just be C12 e to the negative a2x squared e to the negative a2 squared x squared over a1 squared plus a2, I'm sorry, a1 plus a2 squared integral t goes from minus infinity to infinity e to the negative a1 plus a2 t minus mu a1 a2 x squared dt. Change variables. Let u equal t minus mu a1 a2 x. Becomes the integral u goes from minus infinity to infinity e to the negative a1 plus a2 u squared du. And that's just some number, right? Let's call this capital A12. I love this part of the lecture because I really don't give a shit about most of the calculations. I just call it another constant. If I can't, could I actually compute what it is? Of course. It's related to a normal distribution. But I don't need to know. So I get p x of x is going to be C12, A12, and I do know what those are. And I'll have e to the negative x squared. And then I've got a2 minus a2 squared over a1 plus a2 squared. Hey, what does this look like? What does this look like? What shape is this? So we have some constant, e to the negative constant times x squared. It's a Gaussian. Okay, what information do you need to know to identify Gaussian? So what pieces of information do you need to know to identify Gaussian? Come on. What two pieces of information do you need to know Gaussian? It's the mean and the standard deviation. What's the mean? Mean is 0. The standard deviation is. Does everybody agree it's a function of A1 and A2, which are 1 over 2 sigma 1 squared and 1 over 2 sigma 2 squared? And then now what we can do is we can just go through and do the algebra and figure it out. Does everyone agree we could do the algebra and figure it out? Again, this is like the home shopping networking for limited time only. If you're one of the first 4 students in STAP 341 today, we will finish this problem without actually doing the algebra. We know what the standard deviation is. X is x1 plus x2. They're independent. So what's the variance of x? Well, we're doing the more general case. The variance of a sum is the sum of the variances. So what does it have to be? Sigma 1 squared plus sigma 2 squared. So if you do all the damn algebra, you'll get sigma 1 squared plus sigma 2 squared at the end of the day. But there's no need to do it. Because once I know it's some Gaussian, there is only one candidate Gaussian. It's the candidate Gaussian with mean 0 and variance sigma 1 squared plus sigma 2 squared. If you actually do the algebra for what is, you can show that A2 minus A2 squared over A1 plus A2 squared equals 1 over 2 sigma 1 squared plus sigma 2 squared, if I haven't done any algebra wrong. So we add it. Wait, yeah, I'm wondering, did we make a mistake over here? So we add mu squared, then we subtract. And so we're writing this as t minus mu squared. So this was a minus mu squared. Yes, it's a minus times a minus becomes a plus when we bring this out over here, right? This should actually be a plus sign right here. And so over here, when we bring this out, this should be a plus sign over here. So when we pull it out over here, this should be a plus sign. And so then when we put it over here, then there should be a minus sign over there. So I actually got the sign correct over there, but had done it wrong a little bit earlier. And so now we know that it has to be a Gaussian. The only one that's left is this one. And so we know that C12, A12, if you actually do the calculation, is just going to be 1 over square root of, I think, 2 pi sigma 1 squared plus sigma 2 squared. Just when all the dust settles. And again, it's absolutely amazing how well we were able to do this without doing the painful integration. So if you ever really want to appreciate this, try to actually do out all the algebra and all the integration and keep track of everything. Because it's a probability distribution, because it integrates to 1, all I have to do is understand the functional form well enough to just keep moving along. And as long as at the end of the day, it looks like a Gaussian, I know exactly which Gaussian it is. And then all the normalization constants have to mesh and match. All right. Any questions about this? So as you can tell, this is one of the techniques I truly love. It's absolutely wonderful. And so what we've shown is Gaussians are stable. And so it means Gaussian plus Gaussian is Gaussian. Well, maybe I'm just overly excited for no reason. Maybe most distributions are stable. And if you add two distributions with the same shape, the sum is the same shape. Do you think that's true, or can you give me a counterexample where if you add two distributions, the distribution of the sum is not the same shape? Yeah, good, right? The first thing we did today, okay? Uniform is not stable. What else is stable? And one of the things you really need to learn in mathematics is counterexamples or bad cases. Years ago, a student actually gave me a Cauchy distribution, truncated, of course, because it has infinite support. How many of you have seen the Cauchy distribution? This is one of my favorite distributions. And the reason is it's horrible. But you can write it down pretty simply. So P of X is equal to 1 over pi, 1 over 1 plus x squared. So whenever you see a distribution like this, the first question you ask is it a distribution? Yes, it's non-negative. And then it does integrate to 1. That requires a little bit more work. And so to prove that it integrates to 1, we use the following. Yep. Yeah, have we done this? The tangent of arctangent of x is x. And so tangent prime at arctangent of x times arctangent prime of x equals 1. Arctangent prime of x is 1 over tangent prime of arctangent of x. But tangent prime is 1 over cosine squared. So 1 over that is going to just become cosine squared of arctangent of x. But if I draw the picture, if I want an angle whose tangent is x, if I set it up like this, here's my triangle where the angle has tangent x. And so now cosine is going to be 1 over square root of 1 plus x squared. So it's going to be 1 over 1 plus x squared. So the derivative of arctangent is 1 over 1 plus x squared. All right, how does this help? Well, if I integrate 1 over pi, 1 over 1 plus x squared, negative infinity to infinity, this is just 1 over pi arctangent of x evaluated at negative infinity, infinity. Or if you prefer, it's 2 over pi, because it's metric, arctangent of x evaluated at 0 and infinity. So what angle has a arctangent of 0? Well, remember, tangent of theta is sine theta over cosine of theta. So tangent theta equals 0 implies theta equals 0. Tangent theta equals infinity implies theta equals pi over 2. And so you get 2 over pi times pi halves minus 0, which is 1. And this is why I just knew to put the 1 over pi outside. So we can get the normalization constant. All that we need to know is, the integral from minus infinity to infinity of 1 over 1 plus x squared dx converges. It's never infinity, decays like 1 over x squared. So there's some normalization constant. I may not be clever enough to notice that the normalization constant is 1 over pi, but there's at least some constant that works. Okay, so now that we have a distribution like the Cauchy distribution, how many of you have never seen the Cauchy distribution before this class? Okay, what's the first question you're going to ask us? What do you mean? So let's say x is Cauchy. And you can have, you could have a parameterized Cauchy distribution. You could have like x, or let's just do the standard Cauchy. So what's the expected value of x? Well, this would be the integral from minus infinity to infinity of x, 1 over 1 plus x squared. We have a 1 over pi. What should this integral equal? So you're integrating x times 1 over 1 plus x squared. Should equal 0 because it's not a function, right? Sadly, this is not quite true. X divided by 1 plus x squared is not integrable. So we need the limit as AB goes to infinity of the integral from minus a to b of f of x dx to be one answer. This is what it means for a function to be integrable when you go from minus infinity to infinity. That it shouldn't matter how you go to infinity, you should always get the same answer. If I take b equals a, then I'd be integrating from minus a to a of x 1 over pi 1 over 1 plus x squared dx, and that would just be 0. But if I take b equals 2a, I would have the integral from minus a to 2a of x 1 over pi 1 over 1 plus x squared dx, which is approximately the integral from a to 2a of 1 over pi 1 over x dx. Okay, because if a is really, really big, x over 1 plus x squared is essentially x over x squared, which is essentially root of x. So when a is really, really large, the integrand is basically 1 over x. So when I integrate this, I get the log of x evaluated at 2a and a, and I get the log of 2. So unfortunately, the Cauchy distribution does not have a mean. You can try to say the mean should be 0, but it just doesn't quite work. Okay. Now, if x is Cauchy, if we try to calculate the variance of x, that would be the integral from minus infinity to infinity. Well, let's just do the expected value of x squared. One of the key ingredients. That would just be the integral of x squared 1 over pi 1 over 1 plus x squared dx, and that's clearly infinite. So even if you're willing to accept that the Cauchy has a mean, it has infinite variance. So no mean, infinite variance. It does have a median. If you're aware of the median where half the probability is before and half the probability is after, it does have median 0. And so in a lot of questions, it's better to look at the median rather than the mean. The Cauchy distribution is a wonderful distribution of how things might be different if you don't have finite variance. And it turns out Cauchy plus Cauchy is Cauchy. It's stable. Now we have to add a parameter. But anyway. All right, so we've done a lot today. We've done a lot of integrating without integration. For the last minute, I want to just quickly end with the Gregory Leibniz formula. So the integral from 0 to 1 of 1 over pi 1 over 1 plus x squared dx. This is arctangent of 1 minus the arctangent of 0. Let's get rid of the 1 over pi. What's the arctangent of 1? What angle has a tangent of 1? I'm sorry? Pi over 4. Now, I can write 1 over 1 plus x squared as 1 over 1 minus negative x squared, and then use the geometric series formula. 1 plus negative x squared plus negative x squared squared, and so on. And then let's just integrate term by term and pretend that you can justify this. And you integrate from 0 to 1. And you would get 1. When you integrate negative x squared, you would get negative x cubed over 3 at 0, 1. Then an x to the 5th over 5, 0, 1. 1 minus a third plus a 5th minus the 7th, and so on. And here is a formula for pi over 4. Now, this is technically not valid because I can't use the geometric series at 0. So what you technically have to do is integrate from 0 to 1 minus epsilon, and then take the limit as epsilon goes to 0. If you do this, then everything will be rigorous. But here's a nice application on the theoretical mathematics to the Cauchy distribution. It gives you a formula for pi. And what's wonderful is because the terms alternate, if you stop at -1/3, have you overshot or undershot? Undershot, because the next term is positive. If you stop at 1/5, overshot. So not only does it give you a formula for pi, you actually have a sense of what the error is. So it's always nice when you can pull stuff like this out. All right, this is a great place to stop. So again, did a tremendous amount today in terms of integrating without integrating.